Hey there folks, welcome back to another part of my thing where I am making a Tetris data extractor. Well, I did something I thought I would never do. I worked on this off camera, but I didn't do any coding. What I did was, after I went through the previous video, when we ran through the tests one more time to make sure everything was sort of working, I realized I didn't even put the 300 series of my screenshots in the test spreadsheet, let alone the 400 series. If you recall, I played a bunch of Tetris and I got like a whack load of screenshots, and I didn't even put those into the test cases. So that's what we're going to start out with first, is we're going to put all the, well, I put those all in the spreadsheet, but now we're going to run the tests against them, and that's what I didn't do. But anyhow, that's fine. One second here. Let me just, whoops, that's my face. Okay. Okay, so yes, let's do that. So we are going to do what we do all the time here. So we're very close to being done with this first part, even though we're not getting exact perfect results. Hey, this is this is supposed to be, one second folks, when I have a dual monitor set up. Oh yes, host F, right. Things get a little wonky. Okay, so what am I talking about? We're getting very close to a break. Even though we're not perfect in our algorithm, it's good enough to move on to the second part of what I really want to do. And that's, well, I think I mentioned it before, but I'll save it for when we get there. I think I blabbered about it while playing all that Tetris. So what am I talking about with these tests? We had, let's go here into my shared folder. We had integration tests, tests 2, tests 3, and then tests 4. And then we had a test case CSV file with all the test cases. Come on, let's go. Awesome. Test cases. Yeah, so we had the 200 series of test cases, and we had 30 screenshots we analyzed, but we actually have a whole bunch more. And so oh, gross. What am I doing? I'm just going to pull it in. So we're going to delete these test cases. And I'm going to add an existing item. Oh my word. This. These are my new test cases. So we've got 124 of them. So a lot more, but now we actually need the screenshots. So let's do that. Add existing items. So all of the, I actually want to look at medium icons. Here we go. So all of these test cases, except for that screen and that screen, because those aren't game screens, those get added. Okay, and then we're going to do the same thing with the 400 series. I do want to see them though, because there were a few that didn't quite. Yeah, there were a few rocket scenes here. So let's select everything except this one and this one and this one. And that's a beginning screen. Okay, that's it. Add all those. So this is a lot of pictures. A lot of pictures. Yikes. And now we're going to select them all. Shoot, come on. Okay, we're going to properties and we're going to include them. Build action none, copy to output directory, copy if newer. It's a lot of files to include in a project that aren't C# files, so hopefully this won't die on us. Oh, come on, I didn't expect to get tripped up over this. Perfect. Okay. So that's good. Oh, come on. I'm not oh gosh. Not sure what it's doing. I mean, it really shouldn't be that crazy. It's just some test cases. I do want to look at this file. Edit the project file. This is where they all get added, so they're all added here. Oh well, so they're gonna copy over every time we run the program. That's unfortunate, but it's okay. Not every time we run the program, every time we run the tests. That's fine. Okay, so now we're going into our actual test. And this is being we're looking at all of them. So just by adding them to that CSV file, now we can run all the tests. And so this is what we're going to start out with first. And then we want to talk about efficiency based on this result. We're going to talk about what we're going to do next. So let's run these tests. I'm a little bit scared. We had 30 tests before, and now we have 120 some odd. We can watch them execute. And the thing that's really going to drive what we do next are these times. So you can see some of them are taking, like this one took almost 2 seconds to run this. Oh, shoot, this one's taking 2.9 seconds, 3.1 seconds. It's way too long to be of any use for us for real-time game analyzation. Now, this one's almost taking 4 seconds. So the question is, how much of this is the actual algorithm executing, and how much is this like the copying of all the images, the whatever else is running on my computer. I mean, this is running in a virtual machine, so I didn't expect any of that to actually affect anything, but it might be. Only using a third of the CPU. These are significantly longer though. And just to refresh, all we're doing for each screenshot is looking at all the pieces of data. So, holy crap, that took almost 6 seconds. Nothing is taking less than 1.3 seconds. That is nuts. So the other thing we can do is we can run a profiler against this. This will show us where the slowdowns are happening, but I already have it in my mind that I want to make the algorithm more efficient. And there's a really, really simple thing we can do. And that, sorry, I'm just mesmerized by these numbers. The simple thing we can do is the algorithm is constantly doing file I/O as it loads up canonical digit images from the hard drive. And that's something we don't need to do. We keep those in memory. File I/O is among the slowest operations a computer can do. Clearly, this is a lot of stuff happening. And we won't be running these tests like this all that often. 5.6 seconds. So how does it take 5.6 seconds and then the next one takes 1.5? I'm very curious about the report this is going to generate. We're almost done. So my goal is to be able to extract the important bits of information from a screenshot and then make some decisions about it, all in like 1/10 of a second. Clearly these are not 1/10 of a second. We're done. Let's look at our report. I hope it's not very big. Wow. And now the question is, which one of these is a user error? Because remember, I manually inputted this all myself. I don't have a... Here. So 105 was always our issue. 113 was always our issue. That was from before, but let's look at 309. 309. Expected 70 but found 7. See, there we go. That is actually wrong. So that was a user error. That was me. That was me who did that. 309, the 70 needs to be, and this is fantastic. I was hoping we'd find some things like that. So that was an error. This 70 is actually 7. So we'll save that. Now let's look at 432. This one I suspect is legit because it mistook a 2 for a 7, which is what we've seen before. We're looking at the J piece. Ugh. Look at that, gross. I have to forgive the algorithm for getting confused about that. Okay, the next one was 446. And we need to look at the Z pieces. Expected 1, but found 41. Well, no, actually it was 41. So that was another input error. 446. The Z needs to be 441. Yeah, see, I just was firing them off. And I forgot a digit there. So that's awesome. The last one is the J piece on screenshot 460. Expected 17, but found 37. So that's a little unfortunate that it thinks this is 37. But again, I'm going to stress the fact that in 124 test cases, we found issues with 6 of them. And they were all on the piece counts only. And they were all not long bar counts, which of the piece counts is the most important piece count to know. So I think this tells me I'm good, first of all. And what we're going to do now is we're going to make our algorithm more efficient. And we're going to see these things, hopefully, that time to come down. Because our tests were being run in an average of what? 124. Here, let's actually do that calculation. 120, oh, come on. 124 tests, and no, I'm doing the wrong way. 4.2 minutes divided by 124 tests equals 0.03 minutes. Let's get that. So about 2.03 seconds per test. That's what we got. I got to write that down somewhere. 2.03 seconds per test. Okay, done. So first thing I'm going to do is to save all of my changes. Where's my stuff? There it is. All these things are new, so let's add. Git commit. Added rest of test cases. Okay, that's done. So that's saved. All those images are saved. Let us... Actually, I forgot to push that up to the internets. That'll take a bit of time. 27, 28, 29, 30, 31. Okay, so now we're going to look at the very heart of our algorithm, something we haven't touched in months, and that's the actual digit recognizer piece of code. And I'll show you what the problem is, and why I think these tests are taking so long. Almost done. There we go. Okay, so that's saved for all time. See, the good thing is now my computer could get stolen and I wouldn't lose any data. All right, let's close everything. That is not the shortcut I thought it was. Okay, close all. But the pinned ones. Okay. Collapse everything here. So in the data extractor, we have the screen recognition. No, it's the digit recognition. So we got these canonical images, and these were the images that we stole. Well, we took from the emulator screenshots. So they're nice, they're crisp, they're clean, and then we put them through this algorithm that we wrote. So we create a probability list for the thing, you know, how probable is this that it's a 0 or a 1 or a 2, and then we just pick the highest probability, and that's fine. But what we're doing is so let's start here. This is the get digit method. This is where this digit algorithm starts. We reduce the image, so we take all the black space around the image and we get rid of it. Then we create the probability list for this reduced image. And so for each of the digits 0 through 9, we're just going to get the probability that our reduced image is this digit. So inside that method, we called it I? Wait a second. I don't want to call that I. I mean, it's man, my keyboard shortcuts are weird today. We're passing it in I because it's the index of a for loop, but actually in here, I want to call it something else. I don't know, let's just say digit. Okay, so the first thing we do is we get the file name for this digit. And we need the file name because we need to open up the file, the actual image, the canonical image of that digit. So we pad together all of these things and we're literally looking for this file. So if this was 0, we're actually going to choose this file, this 0. And then we're going to make a new bitmap from it. And it's like, well, okay, that's fine, but the process of creating a new bitmap from a path has to open up the file. And that opening up of the file takes a really long time in computer time anyway. So I suspect that the process of doing this, because this has to happen for every digit that we're looking at. So when we're doing the score, for instance, which is 6 digits, we have to open up all 10 digit files for each of those 6 digits. That's 60 file operations for just figuring out the score. And I'm thinking, no wonder this is taking slow. So the solution is to only load them up one time, like just once. And that's what we're going to attempt to do here, but we have to see how we use them. So we open them up, and then we create a new bitmap from the canonical image, a scaled image, because the canonical digit images are a certain size, but the screenshot is a different size. And so we actually scale the canonical image to fit the same size as the digit that you're looking from your screenshot. And then we get the probability based on those two things. So the canonical image is taken from the bitmap using this file name, but it's never actually operated on itself, excuse me. And this is actually fantastic, because what we can do is we can create a dictionary of these things, and yeah, we could just create a dictionary of these bitmaps. So the next thing we have to figure out is, okay, so how are we going to do this? Control home, and that keyboard shortcut's messed up because this is it's a VirtualBox shortcut. Okay. Oh, we don't even scale the image anymore? Oh, wait a second. Oh, I was supposed to use this image scaler, but I didn't. Interesting. I passed it in, but I never used it. One second, folks. The canonical image, oh, wait a second. I do use it here. I reduce it. How did I miss that? 1 second, I have to look at this. New bitmap. You've passed in an image, and then you give it a new size. But this image scaler, you pass in the original, and you give it a new width and a new height. I never actually used this thing, but I can. So what we're going to do is we're just going to actually use the image scaler. Why can't I use it? What did I call it? Oh, scaler. Scaler.scale image, and we want to give it the original, which in this case is the canonical image, and the new width and the new height, which is the character width and the character height. Okay. I mean, that should still work fine. Okay. All right, so here we go. Now that that's fine. We're actually, okay, so we're getting the canonical image using file IO. Then we're scaling it and setting it back to canonical image. And then we're using that canonical image and we're reducing it. So here's what we're going to do. This image scaling is not really necessary. Well, it's necessary, but only one time, right? Because what we're going to do is we're going to open it up from the file, and then we're going to scale it. But the character width and the character height, wait a second, let's follow this character width and character height back. This comes from here. This comes from here, where we actually use it. This character width is the actual bounding box divided by the number of digits. So this character width is always, yeah. Okay, I was gonna say we can just always assume it's the same thing. And as long as your bounding box, which you've set in your actual app settings, uses a multiple of the same multiple of the number of digits, it always will be the same, but that's external to the program. Those are just settings. So I'm not going to rely on those always being the same. So yeah, so that's okay. We don't have to we don't have to worry about that. I was going to save a dictionary of reduced canonical images, but let's try doing this first. Okay, so what we need to figure out is how are we going to use Digit Reader? So where are we going to set up this dictionary? Now we use Digit Reader. We actually register it here. And we register it as an instance per lifetime scope. Do we have to register it as an instance per lifetime scope? And what this means is that every time we ask for a digit reader, we're going to get a new one. Unless we've asked for it twice in the same chain. In the same chain of calls. So our options are two things. Actually, our options are three things. We could make a new class that is canonical image dictionary. That's a possibility. And register it as a singleton. That way the same instance is used everywhere. And that might not actually be a bad idea. The other thing we can do is we can just have a static dictionary on our digit reader. And static variables don't belong to any instance, so it's always there. I can't remember what the third way was, but it was less awesome. So, actually, I like the idea of the canonical digit dictionary. I really do like that for some reason. Okay, let's actually do that. So what we're going to do in digit recognition, we're going to have something called an canonical digit dictionary. And this is an interface. And it's actually going to extend an dictionary. And it's going to be an integer, and it's going to be bitmaps. That's it. And it's going to have a single method called get. And it's going to take in an integer, I. Okay, that's it. That's going to be fantastic. And now we haven't built it yet, but we can actually use the interface in the digit reader class. Canonical images. This is getting to be a long list of dependencies. Oops. So this will allow us to use the same images without loading them from the disk all the time. So now that we have these canonical images, we can actually, instead of creating a new bitmap and this file name, really, we can get rid of these two lines, which we'll just comment out for now and say canonical image equals canonical images dot get digit. Boom. And actually, yeah, I don't think I need to make it a dictionary on the interface, but that's fine. Now you're saying, but we haven't built it yet. We're just using the interface. We actually do have to make this thing. So let's make this thing. Canonical digit dictionary. And I totally spelt it wrong. Canonical. Man, is that even spelled correctly? The word canonical looks funny to me now. Anyway, this is an canonical digit dictionary. Perfect. Let's go back here. I don't even care about it being a diction. Well, no, it's fine. You know what? Never mind. Let's just say canonical digits. There we go. And then in the digit reader, it will be canonical digits. Canonical digits. Calling it canonical. There we go. And then when we use it somewhere down here, which we can never really there. Canonical digits.get digit. Boom. This can be called canonical digits now. Yes. Okay. So now we can implement this interface. Rename what? Okay. Now we can go ahead and implement the interface. Okay. So what we're going to have is we're going to have a private dictionary of bitmaps. And this will be called images. When we make a new one of these, we're not going to do anything except load them up. So for int I equals 0, I is less than 9. Actually, let's not do that. Let's just do this. Do it the fancy way. Enumerable range. Let's go from 0. There will be 10 of them. We're going to select, and we are going to new bitmap. And the bitmap is going to have a path, which we have in our digit reader. At the very bottom, this. Let's copy this. So this is how we're building the path, and we use this path combine method because we don't quite know what operating system we're using. And this is X. And that's a select, and we're going to say .toDictionary. And no, let's do this. ToDictionary. ToDictionary. The X will be the int, and that's our value. So now we're going to say images equals. Okay, so this will take and open up each image, store it in a dictionary, keyed on the integers 0 through 9. We can make this read only. And now if we get when we get a digit, all we're going to do is this, return that. Okay, that's fine. Now, one thing we need to be aware of actually, you know what? Let's cross that bridge when we get to it. Okay, so this will load them all up whenever we ask for a new canonical digits class. And the key is in the registration module, we're going to register this, but instead of, instead of image per lifetime scope, we're going to register it as single instance. And this means just one of these things is going to be built for the entire duration of the running of the program. And I just realized our tests won't reflect this. Because for every test case, we have a brand new instance. That means within a test, so within a certain screenshot, we're not loading up files, dozens and dozens of times. But for each new screenshot, we will actually load up the images 0 through 9 once. Whereas in an actual running, continuous analyzing program, these things will just be loaded up once in memory. So it'll be a little more efficient than what our tests will produce, but our tests should see a dramatic increase in efficiency. So let's just hope that works. Half of programming is just, let's just see what happens. So we've got our canonical digits and we're using them. So this will reduce file I/O dramatically. Let's go back to our test. And it took 4.2 minutes to run everything before. Let's see what happens now. Remember, our average was 2.03 seconds per test. I'm seeing more consistency with the tests. But I'm still seeing the file I/O. Oh, is it starting to? Some of these are the same. Some of them are no change at all. Hey, that one went up. Now it's back down. Oh, we finally got some sub 1 second tests. That's really nice to see. I'm not sure why this one is not running. This one still took 3.4 seconds. So we're better. Ugh, sort of. That helped us a little bit, but not as much as I'd hoped. But you can see some that, like one that took 5 seconds before now takes less than a second. But some that take 1.2 seconds now take 1.3 seconds. So not entirely happy about that. What else can we do to make this more efficient? I'm just going to let that run while I look at my probability list algorithm here. The other thing I'm seeing is that we're scaling the image and then reducing the image, which is, I guess it's important to do it that way so that we get a similarly sized image. Okay, so we're done. It took 2.9 minutes. So if we just do a nice calculation here, 2.9 minutes divided by 124 and then times 60. So we're at 1.4 seconds. Which is better. I mean, arguably we saved over half a second per test just by not doing file I/O. But each test let's go back here. Let's go to our actual test. Let's take a look at our report now. Yeah, so we have 4 issues in those 124 tests. The problem is we're resolving a Tetris data model factory here. And then we are just using it. So what we could do is we could tweak this test a bit. And this is how we're going to tweak the test. It's actually not going to be that difficult. The issue is every time we run the test, we get brand new values for all of our parameters. We build a configuration and we build a container, and then we begin a lifetime scope of the container. We resolve the Tetris data model factory and we create the model factory, and then we just look at the properties, the lazy loaded properties. Whenever we begin a lifetime scope, the container, we're actually building the container right here. If I did that outside of my test, let's do that outside of the test. So let's go private. What is this? iConfiguration and iContainer. iConfiguration, config, and shoot, is that a container? An iContainer. It's an iContainer. iContainer, container. In the one-time setup, we are going to set up these containers. And the config. Okay. So that's going to be done once. So we don't have to do this. And then even though we are beginning lifetime scopes on the container, because our canonical images are a singleton, they span lifetime scope things. So we should, and maybe I should have done this before we made the change to this test, but if we go to canonical digits, this is where all the heavy lifting is done that actually opens them up, opens up each file. Let's make sure I don't have any breakpoints other than the one I want. If I run my tests now, if I debug my tests, we should see that hit once and once only. So let's do that. Let's debug the test. So we hit it, and then we continue, and we'll never hit it again because we've already made it. So that's great. Let's stop. Debugging is not a way to recognize efficiency to get runtime values. So let's just run these tests again. And we don't have to run them all. I just want to see. 1.3 seconds, 1.1 seconds. I'm actually seeing an increase once again of these tests. So that's a little unfortunate. I do see some sub things there. It's not the end of the world. And maybe it's because I'm beginning a new lifetime scope as well. What was our average last time? Our average last time was 1.4 seconds. I think we're under that. Anyway, let's stop these tests. Because actually there's one thing I want to check. And this is where we're going to see the most efficiency happen, I think. I really don't care about any of this stuff. So all I care about is line, score level, and long bars. Those are the kinds of things I'm interested in when I'm actually analyzing a game. Now, I wanted everything because this was called a Tetris data extractor, and they're part of the data, so I wanted them. But for my new plan, a game analyzer with a live feed, I don't need those piece counts. And in fact, I don't even need to calculate everything I want all at once. But let's run these reports without looking at these 6 piece counts. Because each of these 6 has 3 digits, which is 18 digits that has to be compared against 10 other canonical images. So we're making 180 comparisons I don't really care about. Now, how fast does it run? Now it's quite fast. I mean, the biggest ones, I see a 700 millisecond one, but I have yet to see a 1 second one. Oh, see, that was a 1.3 second one. Yeah, a little bit. But this tells me I should be able to analyze a screenshot for important data in about half a second. And if I can do that, I can take a screenshot a second and then make decisions based on that. Seeing a little bit of an increase, but it's not bad. It's not bad at all. The other thing we can do is we can profile this. And what am I on here? I'm getting near an hour here. Oh boy, those last ones took a while. Yeah. I could profile this and we could see what happens, where the actual slowest parts of our algorithm are. And that's actually probably a really neat exercise, which we're going to have to leave that for next time. So I think next time what we're going to do is we're going to put all of this stuff that we have in the tests in the actual program itself, and then we'll profile it and we'll let it run, and we'll be able to see which methods, which statements of our program are actually the most resource heavy, and see if we can address them. This was just a shot in the dark. You know, I think these things are taking a long time. And for the most part, I was right, but it wasn't as big a win as I'd hoped. But nonetheless, getting rid of these extra things or just not looking at them, and that's the thing. Because our data model is lazy loaded, remember, these are nullable integers until you ask for them. Then they're calculated and then stored. So if you never ask for the J piece count, the algorithm's never going to run. But at the very end, if you wanted the J piece count, you could ask for it, and it will calculate it for you. But also the key is it will only calculate it once, because I think we're going to need score and level and lines a lot in our analyzing. It'll only get calculated once. Okay, so these all, well, that's a weird thing, but 1.3 minutes now. So now we're cooking. So I think what we're going to do next time is we're going to profile this to see if we can find any more efficiency anywhere else. And then we should be primed to move on to the next phase of this project. And I may even change the name of the titles of these videos to reflect that. So, okay, that's fantastic. Well, thanks for joining me. Have a good day, and we'll see you next time.